Hi, welcome to online tutorial videos from JCB Labs. For more information and to download the model of this video, you can visit us at www.jcbrlabs.org. We also provide online training, online coaching classes, help in technical assignments. We also do freelance projects based on embedded system, Matlab, machine learning, data science, Python, etc. So if you have any such requirement, then you can let us know by contacting us through our website, which is www.jcbrlabs.org, or you can also mail us at jcbrlabs@gmail.com. So in our last video we talked about how to design a buck converter and how to set the different values of L, C and R in order to get the desired lower voltage. In this video we will talk about so there was certain problem with the design of buck converter, like if we change the R or if we have a different requirement of the voltage, we need to change the duty cycle. So in this video we'll talk about a closed loop PID controller so that we can automatically adjust the voltage, or we can reduce the effect of resistance as well. Okay, so let's start. So let's first go to the basic of buck converter, or just have a look of the buck converter. Okay, so if a buck converter is given by this, we have here a supply voltage and then we have a switch here. Okay, so this switch is a big it's turn on and off at high frequency. Let's set a frequency of F, and here then we have a L, and at the output we have a capacitor, and then we have a resistance here, or we can say the load resistance, and here we have a diode, and at the output of this load resistance we get the output voltage plus minus Vout. So this is capacitor acts as a rectifier, and here's the inductor, and here is the voltage. Okay, so this in the case of buck converter, this V out will always be less than V in, we can say. Okay, that's why it is acts as a step down converter. So in our last video we had talked about what is the formula to select the value of L, what is the formula to select the value of C, and we understood like this output voltage is highly dependent on this resistance voltage, because if we change the value of this R, this buck converter goes into continuous or discontinuous mode. So if load varies, that means if we keep on changing the load, the output voltage may vary. So this is a problem with the buck converter. So we want to remove this particular problem, so that if load changes, there is no change on the output voltage. So that can be done with a closed loop system, and for that we have a different different things, that is the PID controller is used. Okay, so generally PI controllers are used and D part becomes 0. So but we will make a complete nomenclature as a PID. So the block diagram of this structure is like this. We have a reference voltage. Okay, we can say V reference, and the output here we have a PI or PID structure, and then it changes the duty cycle of the buck converter. Okay, so here we have buck converter. So here is the duty cycle of the frequency. Remember we said there is a high frequency there, so the duty cycle of this frequency decides what will be the output voltage. So if we want to fix the output voltage, this duty cycle should change, and we will be checking this output voltage of the buck converter, and the same will go inside this, and yep, and it will be subtracted, and here we got a error signal. So our task will be this PID controller will change this duty cycle so that this output voltage comes to the reference voltage. Let's say if we want the buck converter to produce the output voltage of 5 volt, So this PID will change itself, like so this Vout becomes equals to 5 volt. So if there is any load changes there, or our requirement change, like instead of 5 volt now we want a 10 volt. So this PID will automatically change the duty cycle so that output voltage will become a 10 volt. So in other sense, if we draw a curve of this PID, so let's say this is our reference voltage. Okay, so this PID controller change the duty cycle of the buck converter so that this output voltage becomes equals to this V reference. So this red portion is the output voltage. Okay, similarly we have certain like overshoot, undershoot, all these things are there, so we will understand how to reduce that. Okay, so now let's design the buck converter in Matlab, Matlab Simulink and PID controller in it. Okay, so start with Matlab. So let's see whether recording is being done. Yeah. Okay, so let's create a new model. Okay, so we will design the same buck converter which we designed in our last video. Okay, so for that we need several components. Remember, there are two different blocks in Simulink: sim space and sim power system. So we are using the sim power system components. Remember, sim power component system cannot be connected to simscape components. Okay, so try to avoid it. So first of all we need a voltage source. So let's say voltage source. Search for the voltage source. Here is the DC voltage source, we need it. And then we need ideal switch. So instead of this switch you can use MOSFET. So ultimately MOSFET, it also acts as a switch. So we are taking here a switch directly. Okay, and then we need RLC branch, series RLC branch. Okay, so we'll need 3 of them. We'll change it because we need LC and resistance, and we need a diode. So this diode will be used with this sim power system diode. Yeah, and then we need a measurement. So voltage measure. Yeah. And okay, that's enough voltage measure. We don't need to measure the current because we are dealing with the voltage only. Okay, so now let's, okay, prior to it we need a PWM source. Okay, so here PWM block is available. You just select PWM and we'll get PWM converter generator. So here we apply a duty cycle and corresponding a value, PWM value is generated at the output. Okay, we need that, and then we need this in order to create a PID. Okay, let's first create a buck converter. Let's zoom it up a little bit. Let's connect it, and then we need 3 of this RLC branch. Okay, so now let's change it to L only, and the value of L, we are taking the similar value of a previous video which was 4.8 microhenry. Okay, apply, and we need a diode, so let's flip it. Okay, so here, and this will be connected here. Let's change it to L only, and then we need a capacitor, and the value of capacitor is 3.75 microfarad, and then apply. So we need to rotate it. Let's connect them together. Yes. Okay. Now we need a load resistance R. So generally, let's say our load resistance is 8 ohm. Only then we'll get a desired value at the output. So let's rotate it. Okay, at the across this resistance we'll get voltage measurement. So let's connect this voltage voltmeter across it. At the output we'll get voltage measurement. Sorry. Yeah, that's fine. And now we need a scope in order to see the output waveform. So we need a scope there. And then we need a display so we can check the output voltage as well. Yeah. Let's save it. Yeah. So let's save it on desktop by the name of buck PID. And now we need to design a PID controller. Okay, the output of this will go into the PID. Yes, let's pair this one. We need a constant as a reference voltage as well. Okay, all of this needs to be flipped. Okay, let's change it to minus plus I. Minus plus. Okay, and the output will go here, because remember the block diagram, the output of the PI buck converter will go to the reference subtractor. So that's what we have done here. Okay, so let's take it a little up. Now we will go to the one more thing we have forgotten. We have to add power GUI. So right now we have we are using a continuous mode. Okay, now we will select this one PID. So here we have a PID. So if you double click on it, you will get the value of P and I. So let's put the value 1 as well. Let it remain, because right now we don't know what are the values of P and I. And the output will go here, and it will generate go to the duty cycle, because we are changing the duty cycle in order to generate the PWM. Okay, so it will go to the duty cycle, and the output of this will go to here. So it will change the duty cycle of this PWM generator, and the corresponding PWM wave will be generated that will be applied to the switch. So ultimately we are changing the duty cycle of the switch, which will automatically in accordance with the output voltage. Okay. Now let's change it to, let's say 30 volts. So we are designing a 30 to 10 volt converter. So at the output we will decide how much voltage we want, and let's change this PW, because we have applied 500 kilohertz frequency. So 500 kilohertz is applied here. Okay, Now when we applied 500 kilohertz, it will take a lot of time, so we'll simulate it for 0.01 second so that simulation is fast. Now let's change the reference voltage. Let's say we want a reference voltage of 5 only, and then output. Okay, so let's start the simulation. So if everything goes fine, start compiling. So it is taking too much time even for 0.01 second because sampling frequency is too high. So output voltage nearly 5 volt, and if we look at the voltage waveform, okay, we forget to apply certain things. Go to the scope and do one thing, go to history, untick that one, and go to style and change to the line width to 2, and then okay. So let's run it again. Simulation is done. Let's auto scale it. Yeah, so this is our output waveform. The voltage is very near to 5 volt, but there are high amount of ripples, so let's zoom it up. We zoom it up a little bit. Okay, so let's change the Y voltage x-axis instead of, okay, zoom. We are zooming x-axis only. Okay, so now you are looking at it. At 0 it's taking the overshoot up to near about 15 volt, and then it is coming back down to this one. Okay, and it is having certain ripples, but these ripples are within the range. Okay, but this thing could be a problem, like we are getting a spike of 15 volt. So if we have some sensitive equipment at the output of it, so if we are doing 15 volt spike, so it may damage some equipment. So in order to avoid that, there are several things. Either we change the value of L and C in accordance, or we change the parameter of PID, because right now we have used the 1 and 1 PID, so this may not be the optimal values of the PID. So the next step in this design comes how to obtain the correct value of this P and I, and there are several methods for that. There are Ziegler-Nicholas method, there are several optimization based method, there are several other many different optimization techniques which can be used to get this correct value of this P and I. So we are not dealing with the optimization in this video. So if you want to learn, so you can contact us through our website, or you can mail us at jcbrlabs@gmail.com for the same. Okay, so now let's deal with this only. Now let's say we want, instead of 5, let's say we want a 10 volt at the output, and let's say run it. So this PID controller is working fine, because just by changing the reference voltage, this PID is adjusting itself automatically to generate that particular amount of voltage. So if we go to auto scale, and let's zoom this x-axis only. Now we are getting the output up to this one. Okay, let's slowly. Maximum overshoot is up to near about 22 volt or 21 volt. Okay, so now you know how to reduce this peak overshoot. And let's we can also do one thing. We can see the effect of the change in resistance. In our last video you have seen, if we increase the value of resistance, let's say 30 ohm, the output voltage doesn't follow the input or our design procedure. But in case of we have applied PID, so this PID will automatically adjust the duty cycle so that we'll get the desired voltage there. So let's start it. Yes, we are getting the desired same 10 volt, so irrespective of the load change as well. So that is why this PID controller are important, or this closed loop control is important to design a power supply which remain at a constant level irrespective of load change, irrespective of the requirement of the voltage. Okay, so let's see the output again. Yeah, here. Okay, so our output is around 10 volt on. So I hope you understood like how to design this PID controller for, or how to design a closed loop controller for this buck converter, and how to restrict the effect of this load change and the reference voltage change through this closed loop controller. So if you have any doubt or any suggestion, then you can let us know by commenting below this video. Yeah, and further we also provide online training, coaching classes, and we do freelance project based on embedded system, machine learning, data science, etc. So if you have any such requirement, then you can let us know by contacting us through our website, which is www.jcbrolabs.org, or you can also mail us at jcbrolabs@gmail.com. So that's it for this video. Thank you.